Hello friends, today we are going to solve an example of fixed beam. So we are having a question over here. Analyze the fixed beam shown in figure. Analyze the fixed beam shown in figure using area moment method. So we'll have a fixed beam AB with point load 80 kilonewton and 25 kilonewton per meter UDL, and length of that beam is 6 meter. So we'll give notation C as a center. So as I already discussed in previous video, what are the steps to calculate end moments, fixed end moments we can say. So first what we have to do, we have to assume this fixed beam as a simply supported beam and draw a bending moment diagram for that. In a previous video we have studied individual example of point load and UDL, but in this question we have both of the things together. Point load and UDL both is given. So assume this beam as a simply supported beam. Like this, and draw bending moment diagram for that. So I will draw individual simply supported beam for a point load and for a UDL, and draw individual bending moment diagram for the same. So that diagram is known as a mu diagram. So we are having two loads over here, point load and UDL. So one diagram is mu1 diagram and the second diagram is mu2 diagram. So I will start first with the point load. So this is my point load 80 kilonewton, point load 80 kilonewton, 3 meter distance each. This is C point, and this diagram is, you can say, your simply supported beam with point load. So bending moment diagram for this is, you know that simply supported beam, point load at center, so that is moment at C, moment at center is WL by 4. So here moment at center is equals to WL by 4. So W is 80, L is 6, divide by 4. So that answer we are getting, that is 120 kilonewton into meter center moment. This is A, B and C. So this is 120 kilonewton into meter, that is WL by 4. So this diagram is known as a mu1 diagram. Okay, now I will draw another load, simply supported beam with UDL on entire span. So that is 25 kilonewton per meter, 6 meter span. So whenever simply supported beam, point load at UDL on entire span, your moment at center is WL square by 8. Moment at center is WL square by 8. So W is 25, L is 6 square, divide by 8. So we are getting that answer, moment at center, that is 25 into 6 square by divided by 8. So that is 112.5 kilonewton into meter. Okay, so this diagram is known as, this is 3 meter plus value. Okay, this diagram is known as a mu2 diagram. Okay, so what is the first step? Assume this fixed beam as a simply supported beam and draw a bending moment diagram for the same. This is a simply supported beam with a loading condition, and this is a bending moment diagram for the same. Now next step is what? Assume end moments, couple moments at the ends. For a simply supported beam, assume end moments. So that moment is this is MB and this is MA. Span is same, 6 meter. For this end moment, draw a bending moment diagram. This is MA and MB. We don't have values right now. That values we have to calculate. Okay, so this is my couple moments. This is my couple moments, and based on that moment, I have drawn a bending moment diagram. So this bending moment diagram is known as a mu-dash diagram. So we are having bending moment diagrams. One is this. This is mu1. This is mu2, and this is mu-dash diagram. Okay, so area of mu1 diagram. So what we have to take? Area of mu1 diagram, area of mu2 diagram, and area of mu-dash diagram. Addition of that is 0. In a previous lecture we have seen that is a plus a dash is equals to 0. This is your A diagram. So what is A is area of mu1 diagram plus area of mu2 diagram plus area of mu-dash diagram is equals to 0. Area of mu1 plus mu2 plus mu-dash is equals to 0. So what is the area of first mu diagram? This diagram. What is the area of this mu1 diagram? So that area is a triangle. So that area is 1/2 into base is 6. This is your 6 and height is 120. So 1/2 into 6 into 120 plus what is area of this mu-dash diagram? So we know that for a parabola area is 2/3 into base into height. So plus 2/3 into base is 6. Base is 6 and height is 112.5. Okay, now next is plus mu-dash, area of mu-dash diagram. So here we have MA and MB. Both values are same. Okay, on equal height. So MA and MB are same. So MA rectangle area is MA into 6. So is equals to 0. L into B. So this value is coming 360 plus this value is coming 450 plus MA into 6 is equals to 0. Okay, so MA we are getting is minus 136 kilonewton into meter. So this MA we are getting minus 136. So same for this, that is again MA equals to MB. So MB is also minus 136 kilonewton into meter. So we are getting the answer, that is MA and MB both 136 minus 136 kilonewton into meter. If I draw a bending moment diagram for the same, okay, so that is a combined bending moment diagram for all of this. Okay, so we are having this value A and B surface. So I will draw this bending moment diagram on upward side. So this MA and MB, okay, so that are 136 value minus, I will put a sign over here, that is minus sign. Okay, and because of loading, my bending moment diagrams are these two. Okay, so I will draw a combined diagram for the same. Okay, so that is my UDL. Okay, so that value is 112.5 plus 120. This value is 112.5 plus 120, so we are getting 232.5 kilonewton into meter. Okay, so these two values are negative and this value is positive. Actually this bending moment value is positive and this diagram is negative. This is my final bending moment diagram. So we are having, this is, let us say, E and F. Okay, so we are having these values. Now we are having all distance and loads also. So if I want to calculate at which distance my this bending moment will pass or will cross the line, so point of contrafactual, at the point of contrafactual value, the bending moment will change its sign. So we have to calculate that distance. So we have to calculate this distance up to F. So that's that distance we have to calculate. So how we will calculate that? So for that we want reactions, because this distance how we'll calculate, force into perpendicular distance, because of that value we'll calculate. So for that we have to calculate the reactions. Okay, so how we'll calculate the reaction? So we are having before that we have to calculate draw shear force diagram. So shear force diagram for that is, this is point load 25 kilonewton per meter, and this is again 80 kilonewton, A, B and C value. So what is my reaction? Due to symmetricity we know that RA total load is equals to RA plus RB. Okay, so reaction is equals to, so upward force is equals to downward force. So RA equal to RB is equals to total load by 2. So that is 80 plus 25 into 6. This is a very easy thing. Divided by 2. This is 115 kilo Newton. So each reaction is 115 kilonewton, and we are having these two moments also, MA and MB. So point of contrafracture we have to find. So for a point of contrafracture we have to calculate a distance. Okay, so let us take point of contraflexure. That points are E and F. Okay, so see both values are 136. So that both points change its line from equal distance from both the ends. So let us take this value. This is my one support A. Okay, so assume that point of contraflexure occur at distance x from A. At distance x from A. So this is my, let us say this is my AB beam. Okay, so I am having this moment as a 136 kilonewton into meter. Okay, this is my UDL 25 kilonewton into meter. Okay, so up to my F, let us take this first distance F. So up to F, assume that F is my assumption, the distance I have to calculate. So this distance is x. This distance is F. F is what? This point. Okay, so up to this I am having this UDL. I am not including this point load because point load is at the center. So here your bending moment will not pass through center, so there is no need to calculate that point load 80 kilonewton. So assume that point of contraflexure, let us say point of contraflexure occur at distance x from A. Okay, so we know that bending moment at point of contraflexure will be 0. This thing we know that at point of contraflexure bending moment is 0. So what I have to do, I have to calculate moment at F is equals to, okay, moment at F, we are having this reaction value also. That reaction value is 115 kilonewton that we have already got from the book. Okay, so MF is equals to force into distance. So this is my moment at F I have to calculate. So from left hand side, force into distance, that is 115 into X. Okay, this thing, and this is my distance X, and this is my F. I am having this RA. So RA into X clockwise. See, moment at F, so this RA into X will go clockwise. Okay, so this is RA 115 into X clockwise positive. Okay, again here at this point, at a point, anticlockwise moment is also acting, that is 136. So minus 136, that is anticlockwise. Anticlockwise has a negative, so minus 136 I am including, and up to F my UDL is also there with 25 value, and distance is X, so that is 25 into X by 2, so that is 20 X square by 2 is equals to 0. Okay, so my equation will become 12.5 X square minus 115 X plus 136 is equals to 0. Okay, how you can solve? We have to calculate our unknown, that is X. So X we are getting from the B plus or minus B plus or minus under root B square minus 4AC divided by twice A equation. That's that thing you have learned in your mathematics. So this is a very simple thing. So X we are getting using this equation. X is equals to minus B plus or minus under root B square minus 4AC divided by twice A. This is my A, B and C value. So X we are getting after putting these all values in this equation, we are getting X is equals to 1.394 meter from A. Same from the right hand side. So this distance is 1.394. This distance is 1.394. So up to this distance, 1.394 distance, my bending moment will pass. Okay, so this is all about your first example of your fixed beam using area moment method, where we have to use area of your bending moment diagram, and using area we have to calculate our moments. So this is all about your fixed beam numerical. Thank you.